Our Milky Way galaxy is a vast and wondrous place, a sprawling cosmic city that stretches across the night sky. It is a swirling collection of billions of stars, gas and dust, all bound together by the force of gravity. But the Milky Way holds a profound mystery, one that has puzzled scientists and astronomers for generations. It is a mystery that has captivated astronomers for nearly a century, driving them to peer deeper into the cosmos. Astronomers have observed something peculiar about the way our galaxy spins, a phenomenon that defies our current understanding. The stars in the outer regions of the Milky Way are moving much faster than they should be, according to the laws of physics as we know them. This is unexpected based on the visible matter we can see, the stars, gas and dust that make up the galaxy. Something unseen must be exerting a powerful gravitational force, holding these speeding stars within the galaxy's embrace, preventing them from flying off into space. This mysterious substance, known as dark matter, has become one of the most sought-after enigmas in modern astrophysics, a puzzle that challenges our understanding of the universe. It is a cosmic phantom, invisible to our telescopes yet profoundly influencing the structure and evolution of our universe, shaping the very fabric of space. Join us as we embark on a journey to unravel the mystery of dark matter, a quest that takes us to the very edge of scientific discovery. We will explore its elusive nature, its profound effects on our galaxy, and the ongoing quest to understand this invisible force shaping our cosmos, a journey that promises to expand our knowledge and ignite our imagination. Dark matter is a mysterious substance that makes up a significant portion of the universe. Despite its abundance, it remains one of the greatest enigmas in modern astrophysics. It is invisible to telescopes. Unlike stars and planets, dark matter does not emit any form of electromagnetic radiation. It does not emit, absorb, or reflect light. This makes it completely undetectable through conventional means. We cannot see it directly. So, how do we know it exists? Scientists have inferred its presence through indirect evidence. We know it exists because of its gravitational effects on visible matter like stars and galaxies. These effects are profound and measurable. Imagine a child spinning top. As it spins, it wobbles slightly. This wobble is caused by the distribution of mass within the top. The same principle applies to galaxies. This wobble is caused by the distribution of mass within the top. Astronomers have observed a similar wobble in the rotation of galaxies, including our own Milky Way. Astronomers have observed a similar wobble in the rotation of galaxies, including our own Milky Way. The stars in the outer regions of these galaxies are moving much faster than they should be based on the visible matter alone. The stars in the outer regions of these galaxies are moving much faster than they should be based on the visible matter alone. This discrepancy suggests that there must be some invisible mass, like an invisible hand, holding these stars in their orbits, and preventing them from flying off into the vastness of space. This discrepancy suggests that there must be some invisible mass, like an invisible hand, holding these stars in their orbits and preventing them from flying off into the vastness of space. This invisible mass is what we call dark matter. This invisible mass is what we call dark matter. Its discovery has opened up new frontiers in our understanding of the cosmos, challenging us to rethink the very fabric of the universe. The story of dark matter's discovery begins in the 1930s, a time when the field of astronomy was making significant strides, with Swiss astronomer Fritz Zwicky, a pioneering figure in the field. He was studying the Coma cluster, a massive group of galaxies held together by gravity, which was one of the largest known structures in the universe at the time. Zwicky calculated the total mass of the cluster based on the velocities of the galaxies within it, using a method known as the virial theorem. He was surprised to find that the cluster's mass was far greater than what could be accounted for by the visible galaxies alone, suggesting an unseen component. Zwicky concluded that there must be some hidden mass which he called Dunkle Materie, German for dark matter, lurking within the cluster, influencing its gravitational pull. His observations were met with skepticism at the time, as the concept of dark matter was revolutionary and challenged existing theories. However, in the 1970s, astronomer Vera Rubin made similar observations while studying the rotation of individual galaxies, bringing new attention to Zwicky's work. Rubin's meticulous measurements of the rotation curves of galaxies revealed that stars in the outer regions were moving at unexpectedly high speeds, defying the expectations set by visible matter alone. This further supported Zwicky's earlier findings and provided compelling evidence for the existence of dark matter, a mysterious substance that continues to intrigue scientists to this day. Dark matter plays a crucial role in the structure and evolution of galaxies, including our own Milky Way. It acts as an invisible scaffold, providing the gravitational glue that holds everything together. Imagine our galaxy, a majestic spiral of stars, gas, and dust. Now picture a giant invisible sphere surrounding it, extending far beyond the visible disk. This halo is made of dark matter. Its immense gravity influences the motion of everything within it, much like a cosmic choreographer guiding the movements of dancers in a celestial ballet. Without dark matter, galaxies like ours would likely not have formed in the first place. The early universe was a chaotic and turbulent environment, with matter spread out relatively evenly. It was the gravitational pull of dark matter that helped to gather and concentrate this matter, forming the seeds of galaxies. Section 5. Mapping the invisible, detecting dark matter's presence. Although we cannot see dark matter directly, its gravitational influence on visible matter allows us to detect its presence and map its distribution throughout the universe. One way astronomers do this is by observing gravitational lensing. Imagine a distant galaxy, its light traveling towards us across billions of light years. If a massive object like a cluster of galaxies containing dark matter lies along our line of sight, the object's gravity will bend the light from the distant galaxy. This bending of light, known as gravitational lensing, acts like a cosmic magnifying glass, distorting and brightening the image of the background galaxy. By carefully analyzing these distorted images, astronomers can infer the presence and distribution of dark matter within the lensing cluster. It's like using the shadows cast by an invisible dancer to trace their movements and understand their form. Section 6. Through a cosmic lens, gravitational lensing and dark matter. Gravitational lensing provides some of the most compelling evidence for the existence of dark matter. It allows astronomers to map its distribution on a cosmic scale, revealing the invisible scaffolding upon which the universe is built. One striking example is the Bullet Cluster, a collision of two galaxy clusters. Observations of the Bullet Cluster show that the hot gas from the colliding clusters has been slowed down and distorted by the collision. However, the gravitational lensing data reveal that the majority of the mass has passed right through each other, indicating the presence of a large amount of invisible dark matter. These observations not only confirm the existence of dark matter, but also provide insights into its properties. For example, they suggest that dark matter interacts very weakly with itself and with ordinary matter, primarily through gravity. Section 7. Unmasking the Phantom, the Search for Dark Matter Particles. While we have made significant progress in understanding the role of dark matter in the universe, its fundamental nature remains one of the biggest mysteries in modern physics. Scientists are actively searching for the particles that make up dark matter. They are conducting experiments in underground laboratories and using powerful particle accelerators. One leading candidate for dark matter is a hypothetical particle called a WIMP, or weakly interacting massive particle. WIMPs are thought to be heavy, slow-moving particles that interact very weakly with ordinary matter. This makes them extremely difficult to detect. Other potential candidates include axions, sterile neutrinos, and even more exotic particles with unusual properties. The search for dark matter particles is a challenging endeavor, but it is also one of the most exciting frontiers in modern science. Section 8. A Cosmic Symphony: Dark Matter and the Formation of Galaxies. Dark matter played a vital role in the formation of galaxies in the early universe. After the Big Bang, the universe was a hot, dense soup of particles. As the universe expanded and cooled, dark matter's gravity began to pull matter together into clumps. These clumps of dark matter acted as gravitational seeds, attracting more and more matter, both dark and ordinary. As the clumps grew larger, they began to collapse under their own gravity, eventually forming the galaxies we see today. Without dark matter, the early universe would have been too smooth for galaxies to form. The universe would be a very different place, devoid of the intricate structures and celestial wonders we observe today. Section 9. The Uncharted Cosmos: The Future of Dark Matter Research. The quest to understand dark matter is far from over. Scientists continue to develop new theories and experiments to probe its mysteries. The future of dark matter research is filled with exciting possibilities. New telescopes and detectors are being built to search for dark matter particles with unprecedented sensitivity. These instruments will allow us to peer deeper into the universe and unravel the mysteries of this elusive substance. The study of dark matter has the potential to revolutionize our understanding of the universe. It could lead to new discoveries in physics, cosmology, and beyond. As we continue to explore the cosmos, dark matter will undoubtedly remain a central focus of our scientific endeavors, driving us to push the boundaries of knowledge and unlock the secrets of the universe.